Good afternoon, everyone, and welcome to Science Breaks. My name is Neil Alford, and I'm the Associate Provost at Imperial. And Science Breaks today is about finding life on Mars. A question posed by countless science fiction writers, real science writers, and of course, David Bowie. Now, the NASA Perseverance Rover was launched on the 30th of July, 2020. And it'll descend at nearly 1,000 miles an hour through the Martian atmosphere before retro rockets kick in and reduce its speed. The rover will land on the Jezero crater on Thursday, the 18th of February, a week and 2 days after this event. Amongst the high priority science goals for the Mars exploration are plans to seek for ancient signs of life and collect samples of rock and soil for possible return to Earth. Professor Sanjeev Gupta and Professor Mark Sephton are closely involved in this extraordinary project, and we really look forward to hearing from them. Please do submit questions through the Q&A on the side of the screen. The event is being recorded, so if you want, you can submit anonymously, and you can give a thumbs up to your favorite question to make sure it's asked. So now I'd like to introduce Professor Sanjeev Gupta. Sanjeev is a professor of Earth Sciences at Imperial. He's a planetary geologist, and he'll be studying delta and lake sediments in the Jezero crater to work out the aqueous history of early Mars. He's a team member and a long-term planner for NASA's Curiosity and Perseverance Mars Rover expeditions. Sanjeev, over to you.
Thank you, Neil. Welcome, everyone. It's really a privilege to be here talking about this mission. So as Neil has mentioned, we are just over a week away from the commencement of perhaps one of the most ambitious and exciting space missions ever. And that is the start of a mission to actually bring back rocks from Mars back to Earth, which will just completely change our understanding of Mars as a planet and its geological history going back 4 billion years, but also in that endeavor to search for life on Mars. And Mark Sephton will talk a bit more about that life thing. So it's a great privilege for me to actually be part of the NASA Mars Perseverance Rover mission. I'm going to tell you a little bit about the mission and what we're going to be doing and where we're going to be going. So this beautiful image that you can see of a Martian vista is not obviously at Jezero crater. This is Gale crater where the Curiosity rover landed in 2012. And the goal of that mission, and part of that mission, was to basically discover if Mars was habitable in its ancient past. Today, the Martian atmosphere is very thin, and so long-lasting surface water is no longer possible. So what you see in this landscape is a barren, arid, desolate place. But actually, if you look at those rocks, what you can do is you can envisage a crater that was actually filled with water. This would have been a watery abode, full and probably rained in this landscape. Now, almost 100 years ago, actually people on Earth thought that an advanced civilization lived on Mars. This is actually one of my favorite newspaper headlines of all time from 1911 in the New York Times, where a reporter reported some discoveries by Professor Percival Lowell that the Martians had built 2 immense canals in 2 years. It's just remarkable to think that was only 100 years ago. And obviously that was false. Basically, it was a misinterpretation of telescopic images of Mars, but remarkable to think that this is headline news. Okay, so present day Mars, modern Mars is cold, hyper-arid, dry, desolate, barren, an awful place to live. But actually, Mars, 3.6, 3.7 billion years ago, would have been maybe a wonderful place to live. People think there was a huge ocean in the northern plains of Mars, and there was abundant evidence for lakes and rivers sculpting the surface. It would have been magnificent to have gone and had a picnic on the sides of one of these lakes, basically. So what are the mission objectives for Perseverance? Well, firstly, this is a mission about searching for past life, ancient life, not present day life. So that life would likely be trapped in ancient rocks. So our first task is geological exploration, exploring the rocks in our landing site, trying to reconstruct the ancient environment and understanding the process of formation alteration. That's what my job is. We would then be seeking looking for habitability. Was it a suitable place for life? Mark will talk about this, and biosignatures, seeking evidence for past life. And then crucially, what this mission does is prepare a returnable cache. And by a cache, I mean a returnable set of samples that can be returned back to Earth by future missions. And finally, a goal that I won't talk about is really preparing for human exploration. And there are instruments on board that will help with that objective. So in terms of life, what should we look for? Well, we're not going to be looking for fossil fish. I'd love to find one, but we're not going to find fossil fish, and we're not going to find leaves. But on the right-hand side, what you can see are some of the most ancient evidence for life on Earth, and this comes from the Pilbara in Australia. And these dome-like features are signatures of microbes that were growing on the seafloor and trapped sediment. And perhaps we'll find these, but perhaps more likely in the samples we bring back, there'll be chemical signatures of life, organics. And again, Mark is the expert on this. This is the rover, a graphic of the rover, and we have some spectacular new instruments. The rover is actually built on Heritage. It looks very similar to Curiosity, same design, but has a whole new set of instruments. And I'll talk about a few of those instruments, but in particular, the arm is completely new and a whole set of instruments that help us collect those samples. So firstly, we have the geology cameras, Mars-Cam-Z. I'm on the Mars-Cam-Z team. You can see the two cameras, stereo cameras, multispectral imaging instruments, and we'll use these to basically explore the landscape. We can zoom in on key features, and they'll produce the beautiful panoramas you're going to be seeing in talks for the next 10 years, basically, from this mission. Again, built on Curiosity heritage, and they will help us to decide where to go to search for life and where to sample. We have SuperCam, which is a laser, which is on top of the mast, which will do laser spectroscopy. It will shoot a laser beam and look at the plasma, look at fine-scale mineralogy and chemistry, also look for organics. And then one of the instruments is Sherlock. This is what we'll use to search for organics before we actually sample. So this is deep ultraviolet resonance Raman. And what you can see in the center of this image is the Watson camera, which is basically our hand lens camera, magnifying glass, basically looking at the textures of rock in great detail to look at the sediments and the texture of the features. And here we have the arm that you can see that's been specially designed with the turret, and this has a whole new system of basically drilling. So with this rover, Curiosity drilled rock, not solid rock, but produced dirt samples, basically grindings of the rock, but Perseverance will actually collect cores of rock, basically. So I had to design a whole new set of arm system to do the drilling, and also a system to basically put the samples and store them whilst the rover is crossing the landscape, basically, in Jezero Crater. So here you can see the turret, basically, and on the right-hand side, you can see the different coring bits and the abrading bits. So the abrading is basically a brush, and basically because we want to get chemistry measurements on undust-covered rock to basically get the chemistry before we sample, we have to brush the surface to remove the dust and then look at the raw samples. And then you can see the stabilizers on the turret and the drill bit that comes out and drills into rock samples. And then within the belly of that arm, we have this whole system of storing the samples, very, very specially designed. And basically what we need to do is we need to collect individual samples as we're traversing through the landscape, finding suitable rocks that we want to bring back, the most exciting rocks that we want to build back. We store them on the rover in this system and seal them. And then once we get to a depot site, and I'll talk about this in a minute, we will then be able to individually deposit the samples on the Martian surface that they can be collected by our future mission. Very, very complex engineering here, and amazing design here. So where are we going? We're going to Jezero Crater. So Jezero Crater, you can see on the left-hand side, is kind of in the equatorial area of Mars, and it lies at the edge of this giant impact basin, a huge impact called Isidis that occurred very, very early in the history of Mars, around 3.9 billion years ago. And Jezero Crater exists on the side of that, and is a younger feature, but not that much younger. So here's a close-up orbital image of Jezero Crater. And the key thing about why we chose this site is that we have evidence that Jezero crater, about 3.7 billion years ago, held a lake in its center. And we know this, or we think this, because if you look at the left-hand side of the image, you can see a valley entering the crater and building a delta system out here. And then at the other side of the crater, we have an outlet channel. So water came out of the channel. So for this outlet channel to exist, there must have been water completely filling the crater. So we know that this was once a lake. And lakes are excellent astrobiological targets to search for life. And then the key thing is that we have this delta, this ancient delta, that we can see recognized by this typical deltaic shape over here. And this just shows you the landing ellipse. But also we have some other exciting deposits, what we call the marginal deposits, which are ancient carbonate deposits. And carbonates are, again, excellent places for preservation, formation and preservation of organics and biosignatures. So this is an early geological map that's been produced by the team. And as I said, ancient deltas are fantastic habitable environments where we think that, rivers supplying water to the lake would have supplied nutrients that organisms that might have existed in microbes existing in Lake Jezero might have fed on, or there might have been microbes living on the subaerial surface of the lake. We don't know. We don't have exact models to search for life. And so we have to look at a variety of different environments. But obviously, Jezero isn't a live delta. It's not like this as an ancient delta. And so one of my tasks is really to search for to reconstruct the landscape of that ancient delta and search for the sweet spots where we can search for life. And then that's where people like Mark take over. Okay, so this just shows you the Perseverance landing site and just shows you the landing ellipse, which is an incredible 7.7 kilometers by 6.6 kilometers. And what's going to be happening on Thursday the 18th is we have this remarkable landing maneuver. So we have cruise stage separation, and then we have atmospheric entry. And that's where, after that, we can have no longer any intervention by the engineers, what we call the EDL team, the entry, descent and landing team at the Jet Propulsion Laboratory. Everything's going to be remote controlled by them. The rover system, the whole landing system decides, etc. So we have the atmospheric entry of the rover. We have guided entry, and then we have parachute deployed. And this is the largest parachute ever built, basically. Parachute deployed to slow us down in the thin Martian atmosphere. It's not enough. The Martian atmosphere is so thin that's not enough to slow us down, despite having the largest parachute. We have heat shield separation, and then the radars can take place. We have a whole bunch of radars, and they basically they have maps of Jezero crater, digital terrain models of Jezero crater, and they can basically locate where this descent stage is above the landing site, and basically start positioning the rover, the landing system, to land in a safe place, basically. The terrain relative navigation solution comes in, basically, that allows us to get away from any hazards within the thing. And then we have the powered descent stage where we're, as Neil mentioned, that we have these retro rockets that slow us down, that the parachute is no longer acting, the back shell has been separated. We have the powered descent stage, which is then using the radar to determine how far above we are, and then they deploy what's called the sky crane, and the rover is then deployed onto the surface of Mars on 4 nylon tethers, and then they cut those tethers, and the sky crane, the power descent stage is shifted away, and the rover is successfully landed on the surface. An amazing engineering feat, and this is what hopefully it will be like with a rover safely positioned on the surface. So once we land, we've actually got a few months of commissioning where we get the instruments working, the rover working, make health and safety checks, basically. And then meanwhile, the team will be working out our strategy. And this is one of the strategies, this is one of the drive paths in Jezero crater. And we don't know exactly where we're going to land. So it'll depend on the minute we know where we've landed, the team gets to work on the 18th. We'll be up. The rover is going to land about 9 p.m. UK time. We stay awake all night working out what we're going to do, basically, for the next week. And this is one of the strategies, drive strategies that we're going to do to sample different rock types. And this is a possible cache, basically. You know, what we want to do is we want to return samples back to Earth. They're going to be the most expensive samples ever delivered. And so it's not just the life question. We want to answer questions about the early history of Mars. And so what we want to do is to return a wide variety of samples, basically. And this just shows you the different types of samples. So the lake deposits most might host life, evidence for ancient life. But the crater rim samples will tell us about the early history of Mars, basically, and the rocks that Jezero crater, that Jezero impact went into. And it's the diversity that's most important. And then once we've collected the initial depot of samples and left an initial depot in Jezero crater, the mission will continue collecting samples. We'll drive out of the crater and into this, what we call the outside Jezero area, which is some of the most ancient terrain on Mars. And we will sample really, really ancient rocks to reconstruct that early history of Mars and sample those and leave a second depot behind. And then the choice will be, which depot do we collect? So the sample tubes go into this canister. And what happens is that we are here. It's part of this three-pronged mission that Mark will talk about. We're in the sample collection stage, but around 2027, a mission will be launched that will land on Mars. We'll send a small rover called the Fetch rover that will collect those samples that Perseverance has deposited on the surface, bring them back to the ascent vehicle, which will put these into Mars orbit. And then in 2030, 2031, a new mission, Mars Orbiter, will capture those samples and bring them back to Earth. And that's where a whole new exciting journey begins in investigating in detail those amazing samples in Earth laboratories. So please log in to the Perseverance website. We're on the countdown to Mars, February 18th. We're 9 days away. And we're on the beginning of this extraordinary venture. Thank you very much.
Sanjeev, thank you so much. That was absolutely fantastic and so exciting. It's fantastic. Now I would like to introduce Professor Mark Sephton, who's the head of the Department of Earth Sciences at Imperial. Mark is an expert on organic matter, its detection and characterization. He's an astrobiologist who specializes in recognizing organic records of past life in rocks and will help the team select samples for eventual return to Earth. Now, in recognition for his work, Mark actually has an asteroid named after him, snappily named 7552 Sephton. How amazing is that? Mark, over to you.
Thanks, Neil. So missions to Mars provide lots of groundbreaking insights from the atmosphere to the geosphere and beyond, and Sanjeev's covered some of that. But I would like to talk about astrobiology in the Mars 2020 mission. So the first question is, what is astrobiology? And NASA provide a useful definition. They say that astrobiology is the study of the origins, evolution, and distribution of future of life in the universe. And so for our purpose, we will seek evidence of life on Mars, like a crime scene investigator, like a forensic scientist, looking for the molecular fingerprints of life in the rock record of the red planet. So for life to be recorded in the rock record, the conditions must have been suitable for life to have existed in the first place. And we call this habitability. And habitability involves four components: the presence of liquid water, the solvent of life, the presence of the correct raw materials or the ingredients for the recipe of life, the source of energy, and finally, the time needed for the recipe of life to fuse, to evolve, and to create some sort of functioning biological organism. And so some of the features that Sanjeev described will help us to provide geological interpretations of the Mars conditions that say, this is an environment in which life could have existed. Here is where we need to look for evidence, fingerprints of life. So Mars has changed through time. So there are lots of opportunities for looking for periods of time where habitability would have been present. And so you can see here from this video from NASA that on early Mars, we had the presence of a thicker atmosphere, a wetter environment. And at this period, clay minerals were deposited. And we see clay minerals in Jezero. But over time, the solar wind stripped the atmosphere from Mars because it had lost its magnetic field. It had lost its magnetic protection from atmospheric loss. At this time, the big volcanoes in the Tharsis region were pumping out sulfur-containing gases. These acidified the environment and produced acidic waters, and this led to the deposition of sulfates. And then eventually this atmospheric loss and drying continued, and we had the iron oxide dominated surface conditions that we see at the present day, in which you have to think it would be very, very difficult for life to exist. And you can see here the present rusty red brown planet that we see when we look through telescopes or look from our orbiting spacecraft or from our landers and rovers. So we can ask the question, when is it the best time to look for life on Mars? Well, the older rocks are the best rocks, because in these conditions that deposited the older rocks, habitability was most enhanced. And we can use information from Earth to convince us that this may be a productive venture. Around 3.8 billion years ago, life was present on the Earth, and we actually have evidence of that in various geochemical records. And so if there was life on Earth, there should be life on Mars if conditions were the same on both planets. So when Jezero was created and when Jezero had water, there was life on Earth. So why not, if the conditions were similar enough, shouldn't there be life on Mars as well? But 4 billion years, that's a long time for life, the records of life, to be held onto, to be preserved. And so we need to think about not only habitability and the generation of life, and then the recording of life, but the preservation of that record. Imagine a crime scene again that has not been well looked after. It's been allowed to be exposed to UV light, to water. Those forensic records would have been just lost, and the record would be gone. So we need to think about preservation as a concept. And different materials hold on to the organic records to different extents. And you can see here a table of different matrix materials that could help to host organic signals, but for different levels of time. Ice is very susceptible to change. Just a little bit of warming and your ice and its organic records are lost. Salts are also vulnerable. So if salts encounter water, then they dissolve and the records are lost. But there are some really good materials that can hold on to life's records. And these include silica and clay-rich materials. And you can see here from this colored image of Jezero that there are clays in the lake of Jezero, in the deposits that have been left behind. So we will be looking at those clay minerals to see if they hold on to records of life. And importantly, clay minerals are very good for attracting and attaching organic molecules. And once all that clay is together in an impervious shale type deposit, then they preclude further degradation by oxidants from outside. So we like clays when we think about organic preservation, and we'll be looking at clay-rich rocks on Mars. So the surface of Mars is deleterious to organic records. It will destroy organic records. Time and oxidants are bad things when it comes to preserving organic signals. And you can see here an example of that. We have an organic response from the Murchison meteorite, but also an organic response from very biological materials in a fossil soil on Earth. And both of these start to look the same. So when we take Earth, living organic matter, and then start to degrade it through oxidation and reworking, then it starts to look like non-biological organic matter. So all roads lead to Rome. So preservation really is key. We need to think about all of the ways in which our organic signals will be generated, entombed, and then preserved. So having materials at depth excluded from the surface oxidizing environment is one way in which to preserve them. And impact excavation can bring up materials from the depth and deposit them on the surface where they can be easily accessed by rovers and ultimately scientists. But you've got to think about the process and what that does to the organic records. And some work we did at Imperial College indicated that these pressures involved in impact excavation actually destroy microbial signals and preserve the meteorite signals. And so if we didn't know this process, if we didn't understand the mechanisms involved, then we would make the wrong interpretations. And it's this sort of study that helps us to understand what the opportunity is going to be like when we're looking for the right samples to collect. On Mars, it's always all about the sample. Here's an example of a Mars analog study done on Earth to tell us how to operate on Mars. This is an acid stream, and we looked at the minerals that were being deposited in these sort of deposits that you may find on Mars during its acidic and sulfur-rich environmental conditions. And we sought the organic fingerprints of life in the yellow jarosite, an iron sulfate mineral, and the red goethite, an iron oxide mineral. And we could recognize the microbial mats and the green acidophilic algae entombed and encapsulated in those minerals. So we call this work Mars Analog Studies. And although these places are very chemically exotic and esoteric, they're not always that far away. So this particular extreme acid environment is actually in Lulworth Cove in Dorset, much to the surprise of the locals. So bringing back samples and making sure that the right sample is really field geology. We teach our students to examine their environment, look at the myriad of opportunities that the field provides, but then to choose the best samples using their geological techniques and their experience. So we will use field geology techniques to survey a multitude of opportunities, but again, to choose the best sample. We've got a lot of people to satisfy, a lot of scientists who are eager to understand the secrets of Mars, to unlock the secrets of Mars. And so we need to choose a range of samples and bring the right samples back. And you can see here the sample collection and caching strategy that Sanjeev mentioned. And in the top right-hand corner, you can see some of the early models for equipment for the Mars sample return concept. This was way back in 2010 at a meeting in Imperial College. The Imperial College catering mug is not a piece of the Mars equipment, I should point out. But you can see that we're going to bring back around 0.5 kilogram of Mars rocks in a grapefruit-sized container. Which raises the question, why bring samples back at all? Why not do all of our work on Mars? Well, for decades, we've been going to Mars, taking a limited amount of instrumentation, which is restricted by volume, mass, power, reagents, procedures, to a large amount of sample, the planet itself. We'd like to reverse that. We'd like to bring back an important 0.5 kilogram of sample from Mars and subject it to intense interrogation by some of the most sophisticated instruments and facilities on our planet. And we can also prepare samples. We can do the necessary preparative steps that make those sophisticated analytical procedures even more powerful. So bringing back samples is a multiplier when it comes to the amount of information that you can extract from your target materials. And as Sanjeev mentioned, we will be preparing for future generations in multiple ways. We will prepare for human exploration. If you've got to bring a human back from Mars, you maybe want to think about bringing a sample back first. So that's an important step. We should also understand the hazards that human explorers would find, such as dust. What does it do to our respiratory systems, for example? And we need to appreciate the resources that are available on Mars. And there's an instrument that will seek to generate oxygen from Martian carbon dioxide. And we should perform planetary protection. We should protect Mars from the Earth and also the Earth from Mars. And for future generations, sample return is the gift that keeps on giving. We are still examining at the present day lunar samples that were collected in the 1970s. And so future scientists and future techniques will use the samples that we bring back from Mars in the early 2030s. And maybe some of those future scientists uncover some of the secrets of Mars. And maybe those people are in the audience today. So here's an image that helps to imagine the excitement when the first discovery of Martian biomarkers are found in return samples. And so with this rather inspiring look at what life may be like in future astrobiology laboratories, I'll say thank you for listening.
Mark, that was fantastic. Thank you very, very much indeed. Now we are going to go into a Q&A session, and already we have a number of really interesting questions. So I'm going to pose the questions to Mark and to Sanjeev, and to see how they answer them. So the first question is it also possible that signs of life could be trapped in underground reservoirs or pools, as well as in surface rocks and sediment? Will Perseverance be able to check for this possibility? If so, Sanjeev.
Yep, so that's a really interesting question and something that's been debated a lot during the landing site workshops, etc. So obviously in Jezero crater, we're looking at surface rocks, delta deposits that were deposited in lakes, etc. But when we drive out of Jezero, we'll go into this area outside Jezero, which has these very, very ancient rocks. Now, some of those rocks were probably formed deep underground, have now become eroded and now at the surface. And they may trap evidence for deep subsurface life, and that's one model. We don't really have models for ancient deep subsurface life on Earth. We don't know that life exists in the deep subsurface, but doesn't get fossilized. But people think that potentially those really ancient rocks might preserve evidence for ancient life. And we just have to go and search. Basically, we have no models.
Great, thank you very much. This is an interesting question. Does the lack of a magnetosphere on Mars introduce systematic errors in data collection due to the increase in background radiation? And if so, how can you account for these? Mark, can I ask you that rather tricky question, I think?
So yeah, space exploration has been aware of the increased radiation exposure for decades. So I think when it comes to data collection and instruments for data collection, that's well taken care of. Of course, the loss of the magnetosphere on Mars quite early on in its history was an absolute catastrophe for its habitability and for the potential of long-lasting life. So yeah, the magnetosphere is very important for a number of reasons. But yeah, interesting question.
Thanks. There's an interesting question here. I think it must be from a student, and it's from Kubilay Errol, who says, is it possible to send a rover to the moon with narrow resources? If a group of students would try to send a rover to the moon, would they achieve it? I'm going to ask both of you that question.
Well, that's a great question. What I would do to the group of students is find a group of venture capitalists or a small company. There's all these small companies who are excited and interested in going to the moon. Team up with them. I think it's very difficult to do it by yourself, but I know certainly we have students at Imperial who are working with CubeSat firms, etc., sending little mini satellites into Earth orbit, thinking about going to Mars. So who knows? You start off young, but it might develop into a huge new venture.
Mark, over to you. What do you think?
It's a nice idea. So what we're seeing over the last few years is that the space exploration is almost becoming democratized. It's reaching people in ways that it wasn't before. So the CubeSats are a really good example of how students can get involved in space activities. So sending a rover to the moon sounds ambitious, but why not? We want people to be ambitious. We want them to have lofty aims. And so, like Sanjeev says, yeah, dream big and give it a go. Why not?
That's great. Thank you very much. I have a question here from Arthur Gazeltine, who asks an interesting question. Will Mars ever have commercial interests rather than just the interests of expanding humanity? And I'm guessing we're talking about mineral exploration and so forth.
I think for mineral exploration, I don't think it'll be commercial. I think actually what people looking at Mars in terms of minerals are thinking about is humans going to Mars, and that those humans will be scientists basically and engineers and support. And so we'll be mining resources on Mars, what we call in situ resources, to actually produce oxygen for them to breathe, water, and also enough rocket propellant to bring them back home, because we can't take the rocket propellant to Mars. So actually the mining that we will do on Mars is going to be about keeping humans alive on Mars when we have a human mission. I don't see that there's much talk about commercial, whereas there is commercial activity for asteroids and things.
Thanks. This is an interesting question here. Why are the 3 missions to return the samples to Earth timetabled over such a long period, around about 10 years, rather than much closer together? I'm going to ask Mark that one.
Well, we only have a certain number of windows. So Mars is only close enough to Earth to launch a mission every 2 years. So that cuts the number of years down by half. It's just a function of celestial mechanics. And then you've got to plan and organize for these missions to take place. So there's an inevitable duration involved in these activities. And what you don't want to do with these big, expensive missions is get it wrong. So time spent planning is probably well spent.
Okay, thank you. I think this is probably another one for you as well, Mark. And how do we avoid depositing Earth-originating biological content on Mars? Could this be a problem if it were to occur?
Yes. So there are international treaties that require spacefaring nations to operate under certain recommendations. And so we need to avoid contaminating other planets, particularly for destroying what is a 4 billion year old record that can be interrogated and utilized by scientists to understand better our place in the universe. So we don't want to corrupt that record. And there are what we call planetary protection steps that we take that are carefully calculated. They've been developed since, I think it's the 1950s. I'm a member of a planetary protection working group for ESA. And so we're very careful about those things. And like I say, it's protected by law in international treaties. So you should have confidence in that process. We try our best.
Okay. This is an interesting question. What does the most recent research say about the possibility of past or current microbial life on Mars? What microbes on Earth might look like potential microbes on Mars? I guess that might be for you as well. That's Mark as well, yeah.
So we've had something. So the idea of life on Mars has gone in a couple of directions, both of which are positive. I'll try and explain what that means. On Earth, we've become aware of organisms that live in more and more extreme conditions, and on Mars, we've developed greater understanding of the presence of liquid water in the past. So the probability of life in the past has increased as a result of that. Those two parallel discoveries. The continuation of life to the present day, microbial life, it could have originated at the surface in more mesophilic conditions, more normal conditions, and then found its way into the subsurface into refugia. You know, even life on Earth is thought to have done this in its early days. One of the positive things for present day life on Mars is the presence of methane that's been detected in the atmosphere, and we'll have to see where that research and that discovery takes us. But there are two possibilities that are useful for the idea of life on the surface, in the subsurface of Mars. One is that the methane is biological in origin, and that's prima facie evidence of life. The other is that the methane is evidence of subsurface serpentinization, which is water reacting with rocks to produce methane gas. And even if that doesn't mean that it's life itself, it means that there's liquid water in the subsurface. And so you at least get the habitability step. So for the people who want to believe that there's present day life on Mars, the presence of methane in the atmosphere is a good step forward for them.
Thank you very much. This question is for Sanjeev, I think. In the recent past, there have been dust storms that have lasted for a very long time. If one of these occurs and buries the samples left for collection, will the Fetch rover still be able to find and collect them?
Yeah, that's a good question. So yes, there was a spectacular dust storm in 2018, but actually the amount of material deposited by the dust storms is very, very little, basically. And so they've investigated this, obviously, because what's going to happen is, rather than leaving a canister of samples on the surface of Mars, they're going to leave individual tubes on the surface, because, for example, if you leave a canister and you lose it, you've lost all the samples. So it's better to deposit individual samples at a depot site that are widely spaced, and you will know exactly where they are. And so even if you lose one or two, at least you can collect the others. And they've done modeling studies, etc. And it's very clear that the amount of dust that could be generated in these dust storms will not, in that 10-year time span, will not cover those samples. And they won't be near any active dune fields that are moving, etc. So we've got some clear places that we can safely leave those on the surface.
Okay, thanks. I think this is another one for you, Sanjeev. What would you be most delighted to find from Ingenuity's aerial photographs?
Okay, so Ingenuity is not really a science instrument, it's actually a technology demonstrator. So what NASA want to do is to test powered flight in the Martian atmosphere, basically. It's never been done before. But, you know, I'm somebody as a field geologist. When I go into the field, you know, in the old days, I took my hammer and my rucksack, and these days I take a drone with me because I can get a bird's eye view of the landscape. Now, the timescale we're going to deploy Ingenuity is quite limited. It's going to be shortly after the commissioning phase, so probably in 2 months' time for a short period. But hopefully, depending on where we land, and we're hoping to land basically close to the front of the delta, that's the position we're most likely to land. I'm hoping that we're going to get spectacular views of the scarp, the cliff face of the delta. I'll be able to do Earth, sort of the geology I do on Earth, with those images, but we'll have to wait and see.
That's great. Thank you very much. There's an interesting question here. This is an interesting one. If life forms were to be found on Mars by an unmanned mission, for example, your mission, what implications would that have for any potential plans for future manned exploration?
Oh, I think we would instantly send missions to Mars. We would plan human missions to Mars, basically, because I think one discovery is not enough. It'll probably raise lots of questions. It'll be controversial without question. And so, but that hint, you know, even all the papers that get published on the evidence for earliest life on Earth, they're always countered. There's always a lot of debate, and there'll certainly be debate about any evidence for life on Mars. And so we will send missions and humans to Mars to really interrogate that.
Thank you.
With intense planetary protection considerations taken into account.
Thanks. There's another question which you did mention actually, but it's worth reminding us. It's about the timeline for the Mars sample retrieval following the Perseverance. So just remind us about the timeline that we're looking at. We're not going to see results in the next few months, for example, and we're talking years. So can you just remind us of that, Sanjeev?
Yes, so the idea is that there will be a mission sent to the surface of Mars with the Fetch rover in 2027, I believe, around that time period. And the reason for that is we need to have enough time to actually collect the samples and make sure we've got really good samples. There's no point in sending a mission if we don't have really good samples. So we want to collect a whole diversity of samples that we know are solid, that we will spend the money to bring them back to Earth. The Fetch rover, which is actually going to be built in Britain by Airbus, will retrieve those samples. And actually, if the Fetch rover failed, then Perseverance could actually also deliver those samples to the Mars Ascent Vehicle. The Mars Ascent Vehicle would put those samples into Mars orbit, around 2028, I guess. And then 2030, we would send a mission to Mars, an orbiter mission to Mars, which would capture those samples and bring them back to Earth around 2031, I imagine. So I don't think we'll see samples until 2031, 2032.
Okay, thank you. Here's a question for, I think, Mark. This is an interesting question, this. How will the return samples be distributed to scientists around the world? What's the decision-making process?
So some of that is being discussed, but it'll be the same as previous sample return missions, the Apollo missions and the asteroid missions. The samples will come back, and first of all, there'll be planetary protection. We need to make sure that the release of the samples is safe. And planetary protection studies will generate some science data as well. And then the samples will be curated, and people will write proposals. And based on the quality of their ideas and the potential importance of the science, they will get their samples.
Okay, that's great. Now, I guess this is something that if you've ever seen The Martian, people will want to know this question. How likely is it to grow plants on Mars, and how would they differ from those growing on Earth? I'm going to ask Mark that.
Yeah, it depends. It depends what sort of greenhouse you have, and you would probably need some sort of encapsulated environment. You will need to raise the gas concentrations within there. You need to think about the radiation. Even our own plants have protection mechanisms for the UV so they need light to live, but they also are damaged by the light that they receive. So that has to be managed. So yeah, in this age of GM crops, it would be interesting to see what people could come up with as a sort of self-protecting organism for use on Mars.
Okay, thanks. Now, this is a question here. I'd like to ask, what are the chances that life might have originated on Mars and then brought to Earth via some external interference, for example, an asteroid collision or whatever?
Yes, we have 30 plus Martian meteorites that have arrived on the Earth. So the transfer of material from Mars to the Earth is a fact. It occurs naturally. They tend to be igneous rocks, so not necessarily the sort of rocks that would host life. But it is a possibility, of course. Certainty is always elusive, but it is a possibility that if life originated on Earth if life originated on Mars and it was then transferred to the Earth, that's a mechanism that could work. But what you have to do is ask yourself the possibility, if life simply is the result of the right materials and the right conditions, and Earth and Mars were the same, it's much easier to just generate life, from the recipe of life in situ.
Okay, thanks. Here's a question related, actually. Say we find evidence of life on Mars. How do we know whether it's the same or a different evolutionary tree from what we're familiar with? So in other words, does life originate once and spread, or does it originate individually on two separate occasions? And Magdalena Pfaff has asked that.
So there are ways to tell so it's difficult, if life followed identical routes on both planets, then it might be more difficult, let's say, to say it was multiple discrete origination events. But if life on Mars decided, or by chance, developed a biology based on right-handed amino acids instead of left-handed amino acids, then that would be immediate molecular evidence that this was a separate origination. This was life that originated on Mars and was certainly distinct.
Yeah, I mean, the problem is, of course, it's going to be really difficult to tell. These are very, very ancient rock samples, and we don't really know what's actually preserved. So obviously, looking at the chemistry of these is going to be important, but it might be pretty hard, basically.
Okay, thanks. Now, this is a question for the both of you. As an A-level student hoping to go on to study engineering, how would I be able to have a career working with spacecraft, and what pathways could I have to get me there? So, Mark first, and then Sanjeev.
Well, we're all here, so it's very much available. The UK in particular has a very vibrant and successful space industry. It's enormous. Lots of it is satellites, but it's very active, and we have our own space agency. So you can certainly develop your career in the UK. The world is your oyster. Just develop your skills.
Yeah, I think, as an engineer, get a good engineering training in aeronautical engineering, mechanical engineering, computer science, these sorts of things, and then get internships, chase internships, find the companies. And there's a lot of small startup companies, but also the big ones like Airbus, building spacecraft, seek internships, contact people, go to events, and talk to people, write to people. I became a geologist because I wrote to a professor somewhere saying I was really interested in his work on early life on Earth. And he invited me to his lab to see the mass spectrometers. That was when I was 17. And that's how I got involved in geology. It was purely that visit to a university department and seeing the mass spectrometers and finding about his research in Greenland. And it turned out he was a really famous professor. I didn't know that. I just got interested in something I'd read about him. And that's what got me into geology, basically. So that's what you have to do. You have to seek it out. You have to use your own resources.
That's great. Thanks, Sanjeev. Here's a good question. How do you control the rover from Earth? Do you code a route, or can you control it in real time? And I guess that's one for Sanjeev.
Yeah, so we don't do any real-time relaying, obviously, because it takes time for a signal to go to Mars and come back and get the result back. So what we do is we plan a day of activities for the rover to do on Mars, basically. So at the moment, actually, in the next 3 months, it's going to be pretty terrible for us because we're going to be working on Mars time. So a Mars day is 40 minutes longer than an Earth day. So basically, my shift is going to switch. So actually, next Thursday after the landing, I'm going to be running the first team discussion of where we've landed and discussing immediate things of what we're going to be doing and that's hosting a meeting with 400 people at 4 o'clock in the morning. So I'm not sure I'm going to be very coherent. So what the engineers do is they send a whole set of commands, which the science team work with the engineers in developing, and then the rover, Perseverance, will do them the next Mars day. We get the results back, and then we can plan the next day of activity. So nothing is real time.
That's great. Here's another question, this is a really interesting question. And I'm going to ask both of you this. Is there any possibility of discovering new elements or compounds on Mars that are not present on our periodic table?
Oh, so when we do rover work, when we look at the chemistry of the rocks and we use spectra, what we're doing is we're always trying to match with samples from Earth. So we know that a mineral, for example, with X-ray diffraction has a certain signature in X-ray diffraction, and we match it with mineral libraries on Earth. But it's always not very clear because we're doing it on Mars with limited instrumentation. And so there's not always exact match. So it will be quite difficult to discover something new on Mars. But who knows what will happen when we get these samples back to Earth? Mark is a chemist.
Yeah. So I'd say yes. If biology has been operating on Mars, then organisms, they adapt themselves to their environment, and to do that, to make that step, what they need to do is they need to alter their biochemistry, and that leaves molecular signatures behind in the rock record. And that's my career. I identify signals that tell me, the presence of an organism that occupied a particular environment. And we can do paleoenvironmental reconstruction. From a single drop of extract, I can reconstruct a whole ecosystem. And on Mars, if life originated there and flourished, then the molecular signals that were left behind will tell us something about the environment, because they will have biochemically adapted to that environment. And so no elements, but compounds, molecules, yes.
Okay, great. This is the final question. I think this must be about probably Sanjeev's. How do you test the rover to make sure it functions in the different gravity?
So they have rovers on Earth, and they're scaled basically in terms of weight. So actually, there's for driving, they have a rover at the Jet Propulsion Laboratory, which is called the Scarecrow, which is basically much lighter, and so it's scaled for Martian gravity, and they can drive up steep terrains, etc., to test that. But then they also have for Curiosity, they had a Curiosity double, and we have a Perseverance double that basically carries out the tasks, etc. So that's how they do that.
Okay, that's great. Now, this is the final question, and it's to both of you. Fast forward 30, 40 years, and you are still able to travel to Mars. What's the first thing you do when you got there? Mark?
Well, Mars has, I think it's less than half of the gravity of the Earth. So on a rock-rich planet, I'd do a bit of rock climbing. I'd be much older at that point, and the reduction in gravity would help make up the age difference.
Thanks, Sanjeev.
So the first thing I would do is I would grab a rock or some soil and put it into a bag, just in case of mission failure. Suddenly a Martian attacked me and I had to retreat to my spacecraft. That's what I would do. And then I would get out my deck chair and I would sit down and I would just take it all in, basically. I would take the Martian vista in and enjoy before getting on with the science, basically. I would just enjoy that, just being there.
That's great. Look, thank you so much to you both, Mark and to Sanjeev, for two fantastic talks, and thank you very much for answering those questions so expertly. And thanks also to everybody who sent in questions. So thank you very much. I'd like to just tell you a little bit about the next Science Breaks. That will be taking place on Tuesday, the 16th of March, when Tilly Collins will be discussing urban gardening. So thank you to our speakers. Thank you to you all. Thank you. Bye-bye.